Hi class, this is a pretty fun practice problem for Module 9 in which we're talking both about systems that have chemical reactions and dynamic systems. And this is a problem I adapted and borrowed from Professor Phelps, and it may resemble a popular TV show. So in this problem, we are engineers working in the mythical land of Gatoros, and we have been tasked with conducting a thermodynamic analysis of a recent dragon attack. A fire-breathing dragon has used its flammable breath to attack the gigantic wall of water ice that protects our kingdom from evil invaders. And we need to use our energy accounting principles to estimate the destructive power of the dragon. The wall is composed of water ice. It's 60 feet thick and 350 feet high. The area the dragon attacked is 100 feet wide, and we can model it as an even rectangle. As 60 times 350 times 150 feet. And we have the density of ice. 1 cubic foot of ice is equal to 26 kilograms. We know the specific heat capacity of ice. The local guards who survived the attack informed us that the attacked area of the wall came close to melting and had a temperature of -4 degrees Celsius at the end of the attack. They also mentioned that the attack lasted 5 minutes. The dragon was operating at maximum capacity, and the temperature the day of the attack was -20. So I'm going to first start by identifying kind of given information. So this is going to be really useful to me to calculate the volume of my system. This is the density. This over here is the specific heat capacity, or CP. Let's see, if I continue reading, right here it gives me the temperature, the final temperature at the end of the attack. They mentioned that I don't know if I'll need this, but I'm going to say that T is equal to 5 minutes in case it's necessary. And the temperature the day of the attack was -20 C. So I'm going to take that to mean that my initial temperature was -20. I'm going to assume that the wall of ice had equilibrated, the temperature of the ice had equilibrated with the ambient temperature and was -20 C at the beginning of the attack. Okay. Next thing, as always, is to think about my assumptions for this problem. So if I continue reading, it asks us to write a reduced energy accounting equation, and it tells us some extra assumptions. And so I'm going to start with my assumptions. I'm going to say there are no potential or kinetic energy changes per usual, no bulk mass transfer, no work due to non-flow. I'm going to assume the system is dynamic, because it doesn't mention anything about steady state, and the temperature does change in the system, comparing at the beginning and at the end. Let's see, is there anything else that I am missing? I don't think so. I think that's it. And at least so far in the way it is described to us, I don't think there is a reaction that's taking place in the system. We'll see later that there is a reaction that does take place kind of in the dragon, but not in our system. So if I were to draw my system would look something like this, and the system being that specific piece of wall that is being attacked, and I just have heat transferring in. So if I start with this kind of generic, I'm going to use the algebraic form, because down here it wants me to calculate the total amount of heat release. So I'm going to start with the algebraic form, plus Q plus work due to non-flow. That's equal to the change in total energy in the system. Okay, now this, we don't have stuff that's flowing in and out, so this is 0. and we don't have non-flow work, so that's also 0. And so my final expression would be Q is equal to, and then here it's equal to the change in internal energy of the system, precisely because we don't have any changes in potential and kinetic energy. So this is the final form of the accounting equation that I am going to go with. Okay. So now I can continue working with that equation. So I can say that Q is equal to the change in internal energy of the system. And because this is a solid, I can replace this with, another thing I should mention here is that I'm going to assume constant volume. Okay. So with that, because this is a solid, ice is a solid, I can approximate it by mass of the system times CV times delta T. And remember that for solids, the heat capacity at constant volume is the same as at constant pressure, CP, right here. This is our specific heat capacity of ice. And that's equal to Q. Okay, and now first actually let me calculate the mass of this system. So first we calculate our total volume, 60 feet times 300 feet times 100 feet. All of that was given to us in the problem, and that's equal to 60 times 350 times 100, 2,100,000 cubic feet. And then if I use density, and I know that 1 foot is equal to 26 kilograms, then this would be equal to 5.46 times 10 to the times 10 to the 7 kilograms. Is that right? 60 times 350 times 100. That is right, times 26. Yeah, that's right. 5.46 times 10 to the 7 kilograms, and I'm going to convert that again to grams. So that would be 5.46 times 10 to the 10th grams. Okay, so now I'm ready to go back in here and finish solving this. So Q is equal to 5.46 times 10 to the 10th grams times the heat capacity of ice, 2.09 joules per gram per degree Celsius times, and here we'll go -4 minus, we just move this around, times -4 C minus -20 C. Okay, and if I do all of that math, I get that the total heat that was required was equal to 5.46 e to the 10th times 2.09 times 16, and that's equal to 1.02, really 03, 1.83 times 10 to the 12th joules. Which is a ton of energy, because it really is almost, at least in the same order of magnitude as the energy released by a fission-style atomic bomb. So that is a ton of energy that dragon is releasing against that wall. And it's amazing that it didn't melt. probably because it was so thick, so there was so much mass. Okay, so now let's move on to the next part. We know in this world that dragons spew fire by combusting diethyl ether, a highly volatile chemical, meaning that it can combust really easily, according to the reaction below. Here, dragons are magical and can direct 100% of the heat from their fire breath into the intended target, with no heat dissipation to the surrounding air. The specific heat of combustion of diethyl ether is this, so that means that's... Remember that combustion refers to reactions with oxygen. So what this is telling us is that this is the heat of reaction. This is the change in the specific, this is the specific heat of reaction of this reaction that is taking place inside of the dragon. And the molecular weight of diethyl ether, this seems important too, is 74.123 grams per mole. Okay, now how many kilograms of diethyl ether must be combusted to melt a hole in the wall? Okay, so what this is saying is that this heat in my system, in my original system, which was the wall, was all generated by this reaction. So what it's saying is that the delta H generated in this reaction is equal to 1.83 times 10 to the 12th joules. And remember that to calculate delta H, we multiply the total number of moles by the heat, or the specific heat of reaction. And that's equal to 1.83 times 10 to the 12th joules. So we get that N is equal to 1.83 times 10 to the 12th joules divided by negative 27, 32.1 kilojoules per mole. Okay, one thing that is really important is that from the perspective of the dragon, yes, this is going to be negative 2,732.1 kilojoules per mole, right? Because that's going to be an exothermic reaction. But from our perspective, from the heat that is arriving in our system, that's going to be positive because it is heat that is being applied to our system. Okay, so if I do that, and then this said kilojoules, so I'm actually going to rewrite it in just joules. And so this is equal to, divided by 732,100, a ton of moles, 668,285.9 moles. And then we convert that. 1 mole weighs, the final answer is in kilograms, so I'm going to say 0.74123 kilograms. And so that's equal to 49,535.36 kilograms, which is a ton of diethyl ether. This dragon would have to be enormous to be able to carry that much diethyl ether on top of support its own weight, etc. So it would have to be a huge, huge, huge dragon. Okay, so let's move on to the next part. We have been tasked with rebuilding the wall and adding a new defensive measure to make it impenetrable to dragon fire. We decide that the best defense will be to direct a waterfall to flow over the top of the wall to absorb and carry away the heat from the dragon's fire. The heat capacity of liquid water is this. As an added feature, you set the parameters for your design so that the outflow at the base of the wall will be a balmy 40 degrees Celsius. This way, we can relax in the hot tub temperature water while we laugh at the feeble attempts of the dragon to destroy our defenses. So now we want to determine the volumetric flow rate of chilled water, assuming it starts at 0 degrees, needed for the wall to remain at steady state when being attacked by the dragon. Okay, so the first thing we have to do actually is write a new accounting equation. And so now I can no longer assume, so now my accounting equation does have this term. Right? So now I do know that this is all happening. But I do want this side to be equal to 0. Because I want my equation to be at steady state. Okay? So in this particular case, what we have is this change in enthalpy. This mass is referring to the mass of the waterfall. Right? And in this particular case, we do want everything written in terms of flow rates. So I'm going to change it here. Oh, and this should be specific. And here, right? Okay. So this M is referring to the mass of water that's flowing through that waterfall. And if you think about it, this delta H is the change in enthalpy is a change due to change in temperature, which, remember, for a solid or liquid, we can model that as Cp delta T plus our heat transfer rate, which would be equal to Q divided by T, or time T, and that's equal to 0. Okay? And this mass flow rate, we don't know. This Cp would be 4.2 joules per gram Celsius. This change in temperature would be, and then here, it's important to think that this is a change of temperature of that water, not of the system. And so it starts at 0 and it wants to end at 40 degrees. Right here. Ball me for me 40 degrees. This is the heat capacity of water. Oh, let me be consistent with the colors I'm using to highlight. So 40 degrees, 40, and the heat capacity. So 40 degrees and 0. We calculated already how much heat was released by the dragon. 1.83, or rather by the fire generated by the dragon. And the time, it tells us way at the beginning that the time is 5 minutes. And we want that system to remain at steady state. Okay, so if I solve for this mass flow rate, this it's going to be equal to 1.83 e to the 12th divided by 5 minutes, and then divided by 4.2 and divided by 40. So this is going to be equal to 2.1786 times 10 to the 9th grams per minute, which is equal to 2.1786 times 10 to the 6th kilograms per minute. Since I know that the density of water is equal to 1 kilogram per liter, I'm going to convert these to a volumetric flow rate of 2.1786 million liters per minute. That's my final answer. And this document I'm using right now doesn't have the final updated file for the problem statement, but if we compare these to the information given in that problem statement, where Niagara Falls has a volumetric flow rate of 14.4 times 10 to the 6 liters per minute in a similar, if we were to compare it along a similar width. And so our waterfall, it seems like it would be like a waterfall that's flowing fast, but it doesn't seem super unreasonable because at least it's, maybe 5, 7 or so times a lower flow rate than that of Niagara Falls. So maybe we could go ahead and try to find other waterfalls in the United States that might achieve something similar, and get inspiration from them on how to design our waterfall structure. Okay, but this is a volumetric flow rate that we would need to remain at steady state. Hope you had fun and enjoyed thinking about this problem and thinking about how big the dragon would have to be to carry this much diethyl ether, about how it's the amount of heat that the dragon would need to apply to the wall would be pretty close, at least in the same order of magnitude as a fission-style atomic bomb. And so all of these things point to maybe in real-world physics, all of this would be really hard to achieve, at least with these types of reactions and parameters. Okay, well, thank you, and I'll see you in class.